Hello everyone, my name is Davi Rodrigues and I would like to welcome you to my talk. I thank the organizers for the opportunity to present my work at Trends in Magnetism 2021. I am currently working in a group of Giovanni Finocchio, but I will present works that I developed when I was in the group of Kagomiya Shosita. These projects were funded by these funding agencies. In this talk, I'll introduce two new exotic spinwave effects and topological magnetic textures. These two works can be found on arXiv and might be published by now. Before I start, I would like to motivate these works. An important idea to keep in mind is that exploiting the excitation modes of the topological textures, going beyond the usual approach of considering them as rigid objects, may largely increase their range of applications. Usually, in ferro, ferri, and antiparamagnetic systems, these objects have excitations modes below the Magnum continuum spectrum. Their frequencies are on a range from giga to terahertz. They are of particular interest, for example, for insulated spintronics, where spin waves play an important role for low dissipation devices. Among the topological objects, I would like to point out, for example, magnetic vortices, domain walls, skimions, dynamic droplets, and many others. Recently, many applications have been proposed to incorporate their excitation modes, such as their use as spinwave guides, microwave generators, and in particular for neuromorphic applications such as reservoir computing. In this growing field, we also have suggested a couple more applications such as frequency multiplication and possibly parametrons. As you can see, the number of proposals that incorporate the use of excitation modes is ever growing. And in this talk, I will present two more behaviors that advocate for this growth. My main message here that I want you to remind yourself at the end of the talk is that the interaction between spin waves and topological objects give rise to new physical phenomena. I will focus in particular on two examples. First, I will present the control of bidirectional domain wall motion via linearly polarized spin waves. I will show that by tuning the frequency of the generated spin waves, one can produce the motion away or towards the source of the spin waves. This motion will mostly depend on the frequency of the incident spin wave, going lower for motion away and higher for motion towards the spin wave source. Second, I'll show frequency multiplication in topological objects. In particular, I will demonstrate that by applying perturbations with fractions of the eigenfrequency of the topological objects, it is possible to excite the eigenmodes of these objects. This method presents some advantages compared to the usual linear or even the parametric excitation, where in this case the perturbation is a multiple of the eigenfrequencies. I will start with the first work. For more details, please feel free to check our arXiv. This work was done in collaboration with Professor Kjetil Holst from Norway and his postdoc Akshay Sandbath. In this first work, we explored Kagomiya's paramagnets, such as Mn3Sn. These materials has gained some attention recently due to some peculiar phenomena. As in general for antiferromagnetic materials, they present terahertz dynamics, lack of stray fields, and robustness against stray fields, against external fields. Specifically for Kagomiya antiferromagnets, however, also named as non-collinear interferomagnets, there are a couple more interesting behaviors. Unlike the usual collinear interferomagnets, which are described by only two sublattices, this sort of interferomagnet requires at least three sublattices, implying a more complex long-range order parameter. An important aspect of these materials is the frustration of the interferomagnetic exchange interaction. All these specific properties have shown to give rise to magnetic biofermions and a significant spin Hall effect, for example, which was described in these papers. Moreover, it has been experimentally shown the ability to scan and write domain walls in the system's mere laser pulses. To add to this already impressive list of interesting properties, I want to point out the possibility to control the bidirectional motion of domain walls via linearized polarized spin waves. This behavior is not observed in the collinear counterpart. This interesting behavior, peculiar to Kagomiya interferomagnets, is associated to a frequency-dependent transmission-reflection ratio of the domain wall. We showed via atomistic spin wave simulations that, depending on the frequency of the incident wave, we may expect more or less reflection, which leads to a motion away or towards the spin wave source. This is all due to the momentum transfer between the spin wave and the domain wall. This phenomenon can be elegantly explained by analyzing the spin wave spectrum of the homogeneous magnetic configuration. We clearly show that there is three spin wave bands. In particular, we observe the existence of a flat, non-dispersive band. This means that these bands do not propagate in the material. By studying the interaction between these spin wave bands and the potential due to the domain wall, we see that two of these bands, including the non-dispersive one, are coupled. The conversion from one type of excitation into the other and the resonance of the non-dispersive band produces this effective potential that is frequency dependent. We see that for lower frequencies, we'll have a high reflection ratio, while for higher frequencies, any incident wave will tend to be transmitted. From this, we derive that the transmission reflection ratio dependence of the spin wave leads to a motion away or towards the source in the case of Kagomiya interferomagnets. This was the main message of the first focus point concerning the control of the bidirectional motion of the domain wall. The second work that I would like to present is frequency multiplication in topological objects. If again you want more details, feel free to check our archive. This work is more general than the first one and is related to any topological object, such as schemions, vortices, domain walls. Moreover, it is also valid for ferro, ferri, and even antiferromagnetic materials. This work was done in collaboration with Professor Philip Pigo and his now postdoc Morteza Moseni from Kaiserslautern. We also had a collaboration of Johannes Nothelfer and Ross Knappman, which are PhD candidates in the group of Professor Karin Yamashita, now in Duisburg, Germany. In general, topological objects, which may be a schemion, domain wall, vortices, droplets, and etc., generate a nonlinear potential for the spin wave, a localized nonlinear potential for spin waves. This can easily be seen on this graph made considering a schemion. Here, we consider the excitation of the burning mode of the skinion corresponds to the red line. We applied two different perturbations with different frequencies and show that both of them generate harmonics associated to the nonlinearity of the potential. So here we see harmonics that correspond to twice and 3 times the frequency. However, when the harmonic corresponds to the eigenfrequency of your topological object, there is a resonance at this point, such that the amplitude of the mode is amplified. Therefore, we can claim that harmonic generations allows for frequency multiplications in these objects. An interesting aspect of this method is that this nonlinear process can excite modes of all orders, such that the excitation mode does not have to obey precisely the symmetry of the eigenmode, which is usually related to a selection rule in linear excitation. We also show that it can be more efficient than the excitation with the same frequency. In these graphs here, again, we consider skinions. Here, we show the amplitude of the burning and the elliptical modes as a function of the frequency of the applied perturbation. We clearly see that it's possible to excite these modes with half, a third, and a quarter of the eigenfrequency. Moreover, the amplitude of the eigenmodes is higher than when exciting with the same modes. For here, the burning mode, we show that with half is higher, while for the elliptical mode, all of the frequency multiplications was higher than the linear excitation. An interesting remark is that these eigenmodes are below the magnum continuum. This means that any perturbation excited at the applied frequency dies out and does not generate further instabilities away from the topological object. Another important aspect is that the frequency of the eigenmodes can be tuned by changing the material parameters or by a constant magnetic field. Another remark that I would like to say is that these frequency multiplication only happens in these localized textures. We have shown in our paper that these modes are not able to, this method is not able to excite, for example, the Kittel mode in homogeneous samples, in homogeneous configurations. So we argue that these sort of topological textures are good candidates for immaterial frequency multiplication that are tunable. In summary of my whole work and my talk that I presented here, I would like to say that the direction of the spinwave-driven domain walls in Kagomiya and Paramagnets may be controlled by the frequency of the applied spin waves, as well as the eigenmodes of topological objects may be excited by fractions of the eigenfrequencies. The two new phenomena advocates for their use for their new ways to think about topological objects and how to employ them for spintronic devices. If you need further details, please feel free to take a look at the archives. I now look forward to your questions.